All right, welcome back. I hope you're having an awesome time so far. Our next speaker is Sanjit Paliwal. He is the data scientist at Verizon. Please join me in welcoming him to our virtual stage.
Hello, everyone. Hi, I'm Sanjit. Today, I'm going to talk about the network inventory optimization project that I did at Verizon. So, okay, so this one is not working. Let me go. Okay. So let me go over the agenda for today. So first I'll start with talking about myself and the team at Verizon. Then I'll go over the business problem that we are trying to solve at Verizon, and then go over some of the system definitions that gonna help us understand the system better and the model better. And then I'll go over the first major task in the project, that is the demand forecast. And within demand forecast, we're going to look at the different demand patterns. We are also going to look at the time series, the different time series forecasting techniques that was utilized, and we'll end with the error metrics and the forecast selection criteria. Then comes the next major part of the project, that is the months of inventory optimization, in which we are basically just trying to identify how many months of inventory we are trying to keep for a given device at the central warehouse. And we'll end with the results, and I'll go over some of the major references too. So I'm basically a data scientist at the advanced analytics team for global supply chain at Verizon. I work on analytics proof of concepts, answering questions like what might happen and what should be done about it with the help of AI ML techniques. And basically, we do the end-to-end machine learning process from the business problem formulation to the end product delivery. So, and prior to joining Verizon, I was a master's student of operations research at the University of Texas at Austin. So talking about the business problem, so what we are trying to do is we are trying to optimize the network inventory at the central warehouse in order to first satisfy demand and reduce stockouts, while the second also minimize the inventory cost. So there are basically two major objectives. And then if we look at the block diagram, that kind of explains the system. We have in the center, the central warehouse where the various device units are basically located. And then we have the field locations. Field locations are where the devices are active and they are supporting the customers, our customers. So what happens is there is an outward flow called demand from the central warehouse to the field location. And then there is an inflow of the returns into the central warehouse from the field locations. And I'll go over the details about demand and returns in the next slide. And then in terms of if we look at the second cycle, that is the repair cycle, the defective devices are flowing from the central warehouse to the repair facility. And then what we see is the repair devices coming back to the central warehouse from the repair facility. So this diagram shows the complete cyclical movement of devices within our system. So, and in the next slide, I'll go over the details of this. So in terms of the demand, like you can see, demand could be of two types. First is the maintenance demand, that is certain devices which are active and supporting customers might fail and they need to be replaced by working devices. So that is falling into the category of maintenance demand. And the second one is the provisioning or the new build demand. So new build demand is basically sometimes we are trying to expand a network. We are trying to add new customers. So that would be under the case category of provisioning demand. Then comes the returns. Returns is basically the inflow into the central warehouse. So the returns could be of two major types. The first one is the defective device returns. Like the devices which are failing need to go back to the central warehouse before they are sent to repair. And then the second one is the devices part of the recently decommissioned network. So certain times we decommission certain networks, we do not support certain areas. So that is those devices coming back, and those devices might be working. So we need not need to repair those devices. And then the third major system parameter that we look at is the repair yield. So repair yield is basically the successful repair rate. It is, in terms of mathematically, it is just the successful repair counts divided by the total devices sent for repair multiplied by 100. So that's the repair yield for us. And then the repair turnaround time. So that is the average time in days for a device to return to a warehouse after being sent for repair. And say, suppose, for example, if we say we get one device that leaves the warehouse on January 1st and is getting repaired in the repair facility and comes back to the central warehouse on January 30th. So what happens is that the 30 days would be the turnaround time for that given device for that given repair cycle. So we would say, but what we would do is going forward, what we would do is we would basically take average out those times for that device for a complete year. Then comes the demand forecast. So demand forecast, we first cover the demand patterns. Demand patterns is simply the demand that we see for a given device in our system. So what we are trying to showcase is the different demand patterns that we have. So the first demand is an increasing demand trend. So for a given device, like you can see, in January 2019, we have double digit and even single digit demand. But going forward, the demand increases to even triple digits in the later quarters of 2020. So we can see the demand progressing and increasing over the 2-year period. Then we have the device 2, whose demand trend is decreasing over time. So what we see is like you can see the first quarter, like there are like 4-digit demand, but as we see going down to the later quarters of 2020, the demand is even in single digits. So that's like a decreasing demand trend. And then the third demand trend that we see is almost like a flat, like a constant demand trend that we see. So it's not, if I go over and take the cursor, you could see it's almost, we can draw like a flat line over here, and the values won't be too much higher or too much lower on that. So it's basically almost a flat demand trend. And then the fourth major demand trend that we see is the intermittent demand. Like you can see over here, where I have the cursor, the March 2019 is 70 units. But after that, what I see here is that the first demand that comes in is in June of 2020, that is 4 units. And after that, it rises up. So all these zeros are showing that there is no demand for that device for that period. So this is an intermittent demand, very sporadic demand for those devices. So now what we have here is the different time series forecasting technique that were utilized. So the first one is so what we did was perform univariate time series forecasting demand using the three different models. The first one is ARIMA. ARIMA is autoregressive integrated moving average. ARIMA models aim to describe the autocorrelations in the data. So everybody, most of the people would know correlation. Correlations could be related to 2 different variables and how they change with respect to each other. But what autocorrelation is, the relationship of a variable with itself. So in our case, what it would be in simple terms would be, say, suppose the demand for the month of January 2020 is correlated to the demand for the month in December 2019, November 2019, and October 2019. And now the next method is the ETS, that is the error, trends, and seasonal or exponential smoothing state space models. So these are 2 different terms for the same framework, and the framework contains 30 models like simple exponential smoothing, Holt's linear trend method, or Holt's winter seasonal method, and others. So what this framework does is it basically chooses the right model based on the data. So if the data has just the linear trend, it would utilize the Holt's linear trend method. If the data has seasonality too, it would utilize Holt's winter seasonal method. So different models would be utilized based on the demand. And then the third major time series forecasting technique that we utilized was crosstown model. Crosstown model is it applies simple exponential smoothing on the non-zero elements of the time series and a separate application of simple exponential smoothing to the times between non-zero elements of the time series. So what we are trying to do is we are not only looking at the individual demand level, but we are also focusing on how long it took for a demand to come in. So suppose we are waiting for 8 months for the first demand, those 8 months would also be counted when we are trying to forecast for a given device. And it works, so it works pretty well for intermittent demand forecasting. This method works pretty well for intermittent demand forecasting. Then we have, what we have now is the error metric and forecast selection criteria. So let me first define the terms. Like YT denotes the observation at time t, and FT denotes the forecast of YT. So in our case, YT would be the actual demand and FT would be the demand forecast. So let me first define an error term. An error term, like if I take the cursor YT minus FT, so it's actual demand minus the forecasted demand. And when we divide it by the actual demand and multiply it by 100, we get the percentage error. So the first metric is simply mean of absolute of the percentage error. So this error metric is very common among industry professionals, and what we see is this is very common. But in terms of when we have intermittent demand, when the demand is actually zero, our YT term would be zero. So what would happen is we would have infinite value for the mean absolute percentage error. So to account for this, what we do is we change the denominator. We change the denominator from replacing YT with another parameter that is called the in-sample mean absolute error using the naive forecast. And naive forecast is basically simply utilizing today's forecast for today's demand for tomorrow's forecast. So what we do is, if we want to forecast for February 2020, we would use the January 2020 demand. So like you could see, yi minus 1 would be the demand for the previous month, and yi is the demand for the current month. So this gives us the error, and this 1 over n minus 1 gives us the in-sample mean absolute error. So this mean of the absolute of the scaled error gives us a better metric to kind of observe our performance of the time series forecasting technique when the actual value that we are predicting is zero. So and then it compares our forecasting error with the error from the naive forecast. So that's what's happening over here. And then what we did was the error metric, whether it is MAPE or MASE, is computed by averaging over the test sets. This procedure is sometimes known as evaluation on a rolling forecasting origin, because the origin at which the forecast is based rolls forward in time. So if I take my cursor over here on the image, the red dot is showing basically the test set, and the blue dot is showing the training set. So as the red dot is moving forward in time, the training set is increasing. And what we are doing in this is we are basically calculating error metric for every red dot for every row, and then we are averaging over all the different rows. So we are expanding the training set, and then we are calculating the error metric. So this is a way to kind of estimate the average of, so it is kind of equivalent to the cross-validation that we do in the normal machine learning space. And so what we do in the end is the model with the smallest error metric, and this error metric is the average error metric across all these train sets for a given device is selected in the end. So what we do is we find the smallest error metric across the different methods, RLEMA, ETS, and crosstown, and select the best, the smallest error metric for forecasting. And then based on this, what we had next was the months of inventory optimization. This is the second major task. And this is basically what we did was we created an algorithm that looks at these different parameters that are given on the slide. And it basically tells us how many months of inventory we need to keep. So like in this, the first parameter that we look at is the parts return rate. The parts return rate is simply how many devices we are getting back into the central warehouse in a given month. So if there are enough devices returned that are working or that could be repaired in time to in later on be serving as the demand, then we don't need to have more inventory. So if we have enough returns, then the number of months of inventory should reduce. And then the second metric is basically repair yield rate. Repair yield rate is simply like we defined before, is simply the successful repair rate. So if it is higher, we need to keep lower months of inventory. So it's inversely proportional in this case. And then the third parameter is the turnaround time, the repair turnaround time. So if the repair turnaround time is high, so suppose we are waiting 60 days for the device to get repaired and come back to the warehouse, then we might need some more level of inventory. So it basically just helps us identify what level of how many months of inventory do we need to keep. So that is like it is directly proportional to the turnaround time. And then the fourth parameter that we see is the active installed base trend. So what active installed base trend means is that so we have devices in the network, and the devices that are actually serving the customers, that are the active installed base devices. And if then their number increases with time, that would be an increasing trend. If the number decreases with time, that would be a decreasing trend. So if the number is increasing, we would try to keep more months of inventory in the warehouse. And if it's decreasing, we need to keep less months of inventory. So again, these parameters give us those months of inventory. And as you can see on the bottom, the histogram shows how the months of inventory are distributed for the different devices. So say suppose if we look at this 7 bar with 2900 value, what it means is that 2900 devices would require 7 months of inventory. And similarly, 900 devices would require 8 months of inventory, and so on. So this is kind of showing what the algorithm is telling about the months of inventory to keep. Now, going forward, based on this, we already have the monthly forecast, and now we have the months of inventory to keep. So now we have the results slide. So So what we have is the optimum keep level for a given device is equal to the monthly demand forecast. So how much monthly demand that we have for a given device, and we multiply it with the months of inventory to keep to get the optimum keep level for a given device. And then we have the other metric called the excess inventory for a given device. So what we do is we subtract the optimum keep level from the current warehouse level, and that gives us the excess inventory. So so based on those two metrics, we have the results in the table. And so we have total number of devices that we basically were optimizing the keep level for, that were 83,000 devices. And based on the model that we discussed previously, the number of devices with excess inventory is 7,800 units. And now the excess inventory, so these are 7,800 devices. So now the excess inventory as per model at the central warehouse. So every device would have a number of units. So these 370K units is distributed among those 7,800 devices. So we have total 370K units excess as per the model, and then the potential for working capital reduction as per the model. So potential would be meaning that if we basically take in what the model is suggesting and we kind of remove this inventory from our system, we could save like close to $20 million. So this is 20 million is distributed among these 370K units, which is distributed among these 7,800 devices. And these are the takeaway results from our model. And then I'll go over some of the references for today. So the references were like two major references that I would like to go over. So the first one is the on intermittent demand model optimization and selection. So this is the paper by Professor Nikolaos Korentzis, who worked for the University of Skövde at Sweden and was working on the crosstown model to kind of see how to optimize the various parameters of the crosstown model based on the data. And then the second one is the forecasting principles and practice by Professor Heinemann and Professor Athanasopoulos of the Monash University. And they what they did was they kind of gave the term MASE and the different terms that are used in our project, and it kind of helped us to solve to kind of optimize based on the different parameters of the model that we had. And this is what I wanted to show in terms of the work that we did. And thank you for listening.
Awesome. Thank you so much, Sanjit. That was an incredible presentation, and we really appreciate you sharing these insights with us. I know the audience is giving you a huge virtual round of applause. All right, for the audience, it's time for you to make your way to your next session. Along the way, make sure you accept your connection request and check out our amazing AI exhibits. Thanks so much, and we'll see you around.